We might have already done this one. Have we already done this one? We started doing them, but then you... I think we did this question, but y'all can... Did we do this question? Yeah. I have a solid aluminum sphere, a hollow gold sphere. They're the same mass, same radius. Gold is more dense, of course. Which has the bigger moment of inertia? Stop at 45. 45. Very good. The gold has more mass at larger radii. I is mr squared, and so it has a bigger moment of inertia because r is bigger for a given mass, and since r is squared, it carries more weight, so to speak. All right, 4 T's are made from 2 identical rods. They have equal mass and length. Rank them from the largest to smallest moment of inertia. So the one with the largest moment of inertia will be the one with the most mass at the biggest radius. And the one with the smallest will be the one with the least mass at the biggest radius, and in between. Largest to smallest. Good way to narrow this down is ask yourself what's the biggest and what's the smallest, and then you can get rid of a bunch of answers. A few more seconds. What? 125? I think that's everybody else. All right. Well, I know that A has A has the largest moment of inertia. And I know that because I have a lot of mass at a big radius. And none of these others have that. Okay? I have most of the mass at the biggest radius that it could be at. So if A is the biggest, that gets rid of A and B. So it can't be A. And then which one has the smallest moment of inertia? C, right. So C has, this only goes out to, if the length is L, it only goes out to L over 2, whereas B goes out all the way to L. So it has some mass at a really big radius, but for C it only has a little bit of mass at small radii. So C has the smallest radius, or smallest moment of inertia, so that gets rid of option C. So it's either D or E. We'll go with the majority. I'll go and mark D here. And then in between, it's which is bigger, B or D. And notice that B and D are exactly the same, except for this. Right? I have one length, L, that's rotating around that axis, and in a similar way, I have the same bar for D. But in addition to that, I have this extra bar that's also rotating around the axis. So D then has a bigger moment of inertia than D. So it makes D the right answer, because it shows that D is bigger than B. Okay? All right, here's a student holding a meter stick with some masses dangling from it. Rank in order from difficult to least difficult. Keep it from rotating. That is the most torque to the least torque for these. You can probably just reason it out, or you could actually calculate the torque for each of them.
I'm confused with the question.
I want you to those masses are exerting a certain amount of torque on each meter stick,
Okay.
which is the most torque to the least torque. Rank them from the most to the least.
I'm talking about, what do you mean by rotating? Keeping it balanced like this?
From moving, like, pulling down.
Yeah, so see, it's rotating about this axis
Oh,
of a force acting here.
yeah, that's what, okay.
Yeah. .145, I'll stop. That's right, yeah, E is the right answer. A, not sure why I'll put A, let's see. I know that C is the biggest one because it has the most mass at the biggest moment arm. In fact, you know, I can calculate the torque. I'll sort of do it without units. I'll just do M times G times R. We'll take this to be 1 meter, in which case the torque, just leaving out the G, is going to be 1,000 times 1, so it's 1,000. Here it's going to be 1,000 times 0.5, which is going to be 500. Here it'll be 500 times 1, which is 500. You see what I'm doing? I'm not using real units. I'm just sort of getting a relative scale. And here I'm going to have 500 times 0.5, that's 250, plus 500 times 1, which is 500. So that's 750. And then so I have a relative scale for them. The biggest, the next biggest, and then these two are equal. I can see these two are equal because I have twice the mass here at half the moment arm, and then half the mass at twice the moment arm. So those two cancel out. Those give you the same torque. So E is the right answer. Yeah? Yeah? All right, moment of inertia is which of these? And this is our I, moment of inertia. Forty-five. A is right. Remember, mass is a measure of inertia. Moment of inertia is also a measure of inertia. A rigid body is in equilibrium if which of these is true? Stop at 1 minute. Oh goodness.
All across the board.
Okay, remember in chapter 4 we dealt with this. We said that it's an equilibrium if this is true. And now in chapter 8, we're saying also this needs to be true. And so the answer is E, both 1 and 2. Well, we'll deal with this in the next chapter. We'll do quite a bit of this. It's not in your book yet, but we'll deal with static equilibrium quite a bit. Okay, if we have complicated systems, like a building, for example, you have forces acting, but you also have torques acting on that body, and so you have to consider both the forces and the torques that are at play. Gives you an extra set of equations, so you can find out a lot more information. Rank these by their torques.
The little dot is the.
Yeah, that's the rotation axis, the dot. Yeah,
Okay.
they pivot at the dot. Stop at 2 minutes. 2 minutes. I'll give you 5 more seconds. 2:05. Just guess if you don't know. Oh, did you get it in? Oh, I'm sorry. Let's see. A is right. No, this is a good test-taking skill, actually. You could look at this and pick out some things. First of all, I know which one has a torque of 0. C has a torque of 0. Right, so because the angle here is 180 and the sine of 180 is 0. But, all of these have torque C as the smallest, so that doesn't really help you. But I can also say which two have the same torques. Right, because this one has half the force, but at twice the moment arm of this one, which has twice the force at half the moment arm. So torque A is equal to torque D, and the only one that has that is A. All right, so that's the only one that has that. So, and then which has the biggest is E. Now I know that here my torque is 4 newtons times, let's just say it's 1 meter times the sine of 45. But the sine of 45 isn't a half, it's bigger than a half. It's like 0.7 something, 0.71. Right, so you have to be careful with that. So it's going to be bigger than the torque offered by this one right here. Right? So anyway, with that information, A works out to be the only right answer. All right, that's the end. So you'll see questions similar to that in the multiple choice, ranking torques, ranking moments of inertia, questions along that ilk. I would study the concept test. I think I've updated the concept test, but it includes things about momentum, and you won't see momentum or energy on the test next week on Monday. It'll be about 10 multiple choice questions, 4-ish free response questions. It'll be worth 90 points. I'll give out the test at 7:15, just like we did last time. I think that worked pretty well. But it'll be an hour exam. Like I'll expect you can finish in an hour. So if you want to come at 7:30, you'll have ample time.
Is there a way that you can go in the homework and tell us which one?
Yeah, of course. Yeah. And would it help to send out an email about the old test questions
Yes,
later?
that
Yeah.
would- I know you had that one, but I don't know if it's updated from.
Yeah, I can, well, that one includes all of chapter 8, so. Well, let's just look at the homework right now. So number 1, you will have a cross product. It'll probably just be a standalone problem. Number 2, number 3, number 4, number 5, number 7, except not energy. Okay, so like number 7, and then that's all. On number 7, this is one of these problems where you have to say the torque equals I alpha, and then solve for alpha, and then say omega equals omega naught plus alpha t, and then find the final angular speed. And then in this problem, you had to go on and use that and say the kinetic energy is 1/2 I omega squared. You won't see that part, but you will see the application of Newton's second law and the kinematics portions of those problems. Okay? Is that clear? Any questions or any still sort of murky points about chapter 7 or this portion of chapter 8?
On that one, you're saying that you need to find omega. Why would you need to find omega if you just found out? Or not omega. Did you say theta or omega?
Omega.
Oh,
Yeah, not theta, not in this case.
Not
But
in this
you
case.
could have a problem where I ask you, well, how many revolutions does it go through, or what is the displacement?
I misheard you.
Yeah. Okay. You need to be able to read problems and pick out the appropriate information for those kinematics.
And then all of chapter 7.
All of chapter 7. And that included kinematics. Oh, no, it's kinematics. Right? Oh, and centripetal forces. Centripetal forces. So you do need to be able to look at the system and tell what is the centripetal force at play. Is that clear what I mean by that? Let's just do a quick little look. So for example, let's say that I have let's say that I have a ball on a string and it's going about in a circle like that. We worked.
What FT is?
Huh?
We're going to try to figure out what FT is.
Right, yeah, something like that. So for example, if the ball is up at the top, if I draw all the forces on it, I have Fw acting in that direction, and then I have Ft also acting in that direction. In this case, I would say the sum of the forces is Fw plus Ft, and that's going to equal mv squared over r. Okay, and I could ask you a variety of things, like I could give you the speed and ask you what is the tension in the rope or something along those lines. Now, similarly, let's say that the ball is down here. In this case, it's a little bit different. I have my weight in this direction, and my tension upwards in this direction. In this case, the sum of the forces would be Ft minus Fw, and that would equal mv squared over r. And you could solve for any number of things. What's the tension if you know the speed, or what's the speed that would cause the string to break, or something along those lines. We had similar problems too, where we had, say, for example, a car going around a curve. We worked a problem like this in class. I think you have one in your homework too. A car going around a curve. The right, Fs is equal to our mass times our centripetal acceleration, or centripetal force. Also, we had a deal, I don't think you'll see this quantitatively, you won't see this quantitatively, but we did work through a problem, and you should just sort of look back over it. But you won't see it where you have to work it as a free response, but you could see it in the multiple choice, where you have a car that's going on a bank curve. Remember, in this case, our centripetal force was not just the static friction, but it was also provided by what?
Normal force.
The normal force, right. So we had components of the normal force and the static friction in the x direction that acted as our centripetal force. So that's why they make bank curves, so that you can go faster on them, because it's not just static friction that's holding you on the road, but it's also your normal force. The road is actually pushing back on your car to make it go around that bank, that curve.
Physics breaks and your car goes flying across.
Oh no, you drive too fast and you go flying across into the body or whatever.
That's really cool. That'd be a cool movie thought. Physics start going all out of whack and all
Right,
the things
right.
that are like, it's like you drive down the road, all of a sudden your car starts flying. It's like,
Right.
what? This physics don't
You would see a problem, calculating the centripetal force. And it's really a matter of identifying which is the centripetal force. All right? One kinematics problem, centripetal force problem, a Newton second law problem, and then, probably another one of those. Or just three problems. I'll probably four. Huh? Oh yes, a cross product. Yes. That's it. Let me go write that down. Because that should tell us. All right, folks. That's easy enough, right? It's a lot easier for me. Like,
Say
you all
are
make it.
easy are the ones that is.
Huh?
The ones you say are easy are the ones that get me.
So it is a lot easier for you if we all make A's.
It's a lot easier, right? It's easier for me if you all vomit and like don't write anything, or if you all make A's. And then because I can just flip through pretty much. Can y'all do that?
So you're gonna say it's
I'll
right.
just put the watermark and we'll,
Okay, any other questions?
So you're gonna say after I vomit, it's right, even though there's no.
Come on.
you can do
Okay.
that.
Any questions, Joe? All right, we're gonna have this little. It's like a test appetizer. It's just like 10 points.
It's your entree. Would you like to eat entree?
Okay, I've already
Yes, I'd
told you
like
what's
10
on it,
points. Entree.
if you want a few minutes to look over, you have one on this side, the cylinder, and one on this side, the bar, the table's on the back. Whichever one you don't want to do, just draw a big X through it, and you can choose one. All right, some sort of spread out a bit. But if you want a few minutes to look over it, I'm going to go that too. We have 20, 25 minutes. So you can take a few minutes if you wish. You want to go ahead? Everybody wants to? You like yours? Yeah, why don't you put yourself on C? Huh? Just do one. Just choose one that you want to do. It's worth 10 points. These 10 points are for your test, not mine. Where I got one? Let me know when you're ready.